Okay, hello everyone. This is Professor Lee again. We're going to do another lecture. So before you follow this lecture, please download those PowerPoint file from our E360 website, the resource section. Either print the PDF file and have it with you while you're watching this video lecture so that you can take notes and if you have to, right? That would be most helpful. Okay, so today we're going to talk about chapter 3 part B. We're going to talk about measures of distribution shape, relative location, and talk about outliers, and we're going to talk a little bit also about the weighted mean. Okay, so let's talk about the relative location. Well, I guess the question goes something like this. Let's say you have a bunch of data points in all different forms, right? You have a bunch of numbers. Now, some of those numbers might be close to the very middle number, let's say mean. Some of those numbers can be very close to the mean. Some of those numbers may be quite far away from the mean. Now, so however, if your mean is if mean itself is in a different size and different magnitude, then of course it's kind of difficult to see the position of each data relative distance from the mean. So what they suggest, they try to make it standardized. They try to make each data point a standardized point so that it has some type of uniform meaning. That's what they are trying to do, and that's basically what the z-score is all about. Right? That's basically what the z-score is all about. So the z-score is what? Z-score is a standard score. You know, all different data points have different size and shape. They're all very different. But if you standardize those data points into what's called the z-score, then it's a lot easier to see the relative position of each data point from the mean, right? And so how do we do that? Well, this is the formula right there. So z equal x minus x bar over s. So what's x bar? Now remember that this is open note, open book course, but I rather want you to memorize a certain symbol, and x bar is one of them. X bar is sample mean, right? Sample mean. So this x right here refers to each individual data point. Now to that, you subtract the mean and you divide that by s. What's s? S is sample standard deviation, right? Sample standard deviation. So z-score of an observation, a z-score is a measure of a relative location of the observation in the data set. Now it's kind of not that easy to understand, so let me actually try this. Let's say you have data point. Let's say 1. Oh, let me adjust 1 and 5 and 9 and say 4, 6. Okay, let's say you have these data points. Now, let's say this is a sample data. So let's say this is sample. Let's find the X bar, mean, first. If you find the mean, that would be 10, another 10, 20, 25. 25 divided by 5. So mean would be 5. Mean would be 5. Now, how do you find the standard deviation? Standard deviation, S square, we have to find the variance first. That would be each individual data point, say 1 minus the mean square plus 5 minus 5 square plus 9 minus 5 square plus 4 minus 5 square plus, say, 6 minus 1 square over, let's say we have 5 data points, so it should be n minus 1, so that should be 4, right? So, if you have calculator, I want you to calculate this with me. So if you do that, let me see. Let me open my calculator. That will be negative 4 squared, so 16. That will be 0. That will be 4, so 16. So that will be 1 plus, that will be, 6 minus 5. I made a mistake here, right? That should be 5 there. So that should be 1. Enter. Divided by 4. So answer that I got is 8.5. 8.5. Now you need to find S. S would be square root of 8.5. So square root of 8.5 would be 2.915. You can just say approximately 2.92. Now, we have these data point. Now, where's the mean? Mean is 5 as we calculated here. So, this number 1, this data point, how far is it from the mean? This 5, how far is it from the mean? Well, there's no distance, actually, it's itself. This 9, how far is it from the mean? This 4, how far is it from the mean? 6, how far is it? Where is the relative location of each data point? Well, and how do we find that? Well, according to this z-score formula. This is the formula that we can find the relative position, which is called the z-score. So how do we do that? X minus x bar over s. So if we go back to that blackboard, now we know that the z-score formula equal x minus x bar over s. So, our z-score, the first one, 1, right here. So, for x equal 1, we have z-score would be 1 minus 5, because x bar was 5, over 2.92. So what would that be? That would be negative 1.36. Now we have this z-score 1.96 for x equal 1. What's x equal 1? I'm talking about this data point right here, right? This data point. So this data point right here, the value was 1, but what does 1 really mean in terms of the relative location? That 1 is actually, as we calculate, it's negative 1.36. So the relative position for this z value is going to be negative 1.36. What was the x value? X value was 1, right? It's 1 here, right? X value was 1, but if we convert that into the relative position, now it becomes negative 1.36, right? And that's what they are doing in this slide. Okay. So, and we're gonna do an extensive study on this z-score in chapter 6, right? Now let's talk about the Chebyshev theorem. So Chebyshev theorem is kind of a little bit difficult, confusing to understand, but very easy to apply. And that might be a good news, right? A little bit confusing to understand, but very easy to apply. It says at least 1 minus 1 over z square of the item in any data set will be within z standard deviation of the mean, where z is any value greater than 1. Whatever that means, right? Whatever that means. So that means something like this. Let's say, they say that 75% of any data set must be within 2 standard deviation of the mean. Well, where do they get this 75 and the 2? Well, that's actually from this formula right here. Right? This formula right here. Now, let's replace this z by 2. Let's replace this z by 2. Then what does that become? Well, let's see. It was 1 minus 1 over z square, right? So if we go back to the PowerPoint slide, that's the formula that I just wrote. And this next slide, it says 75% of any data must be within z equal 2 standard deviation of the mean. So where do they get this 75%? Well, if you replace this z, oh, you know what? Okay, replace this z by 2, then you have like 1 minus 1 over 2 square, which is 4, which is 3 over 4. What's 3 over 4? That's 75%, right? So remember in the PowerPoint, it says 75% right here. Where do they get 75%? They get from that formula, 1 minus 1 over z square, and they replace z equal 2. That's how they get 75%. Where do they get the second one, this 89%? They get this 89% by replacing that, this formula right here, replacing that z, right, this z into 3. And that's how they get 89%. And if you replace that z by 4, that's 94%. So you kind of understand these numbers, but what does that really mean? That means something like this. Regardless of any distribution, 75% of entire data must fall within 2 standard deviation up and down from the mean value. That's what I mean. So if you know your mean and you can set up an interval, which is well, you have to know your mean first. Then 2 standard deviation up from the mean, 2 standard deviation down from the mean will form an interval. Now that interval will surely cover at least the minimum 75% of any data. What's any data means? Any type of shape. It doesn't have to be uniform, or it doesn't have to be nice, normally distributed. It could be seriously skewed left or skewed right. We don't care, as long as it has certain distribution. Then at least 85% will fall into this interval, right? 2 standard deviation up and down. If you want to figure out the 89% interval, you don't go 2 standard deviation up and down, you go 3 standard deviation up and down. And for 94%, you go 4% student the standard deviation up and down. Okay. So let's do an example. Remember the apartment rent problem that we've been following from the previous lecture? We had a bunch of different numbers. Now, if we let the standard deviation not as 2 or 3, which is the example that we had here, but if we want the not the 2 standard deviation away, or not the 2 standard deviation away, so that you have 75%, not the 3 standard deviation away, so that you have 89%, not the 94 for 4 standard deviation. What if you want 1.5 standard deviation away? Then what do you do? Then you just simply need to replace that z by 1.4, 1.5, and you form these numbers. So if you replace this z by 1.5, then it will be 1 minus 1 over 1.5 squared, which gives you about 56%. So what does that mean? That means something like this. 56% of entire data set must be between, must lie in between 1.5 standard deviation up or down from the mean. Look at this. So this mean value, $490.80, right? If this is money, right? 490.80 minus 1.5 times standard deviation, 54.74, then it forms this number. If you do x bar, which is the mean, plus this time 1.5, s, then we have 573. We have another number. So this interval, the small number being this interval, will cover minimum at least 56% of entire data set. Now, remember, this is the minimum requirement. In fact, if you actually calculate it more, with the more accurate technique, you can see that actually 86% of rent value are between these two numbers. But we have to study a little bit more to actually figure out that. For now, for us, we know that minimum requirement for those interval would be 56%. Now, empirical rule is very, very similar to that Chebyshev. It's very similar to Chebyshev. Empirical rule can be used to determine the percentage of data value that must be within a specific number of standard deviation of the mean. So empirical rule is based on the normal distribution, which is curve, which will be covered in chapter 6. So Chebyshev rule is a bigger concept. It happens for any type of distribution, size and shape. But the empirical rule is actually mainly dealt with in chapter 6, and so far we have a little bit of a homework, and the empirical rule is a little bit more stricter than the Chebyshev. Chebyshev is a little bit broader. So according to the empirical rule, one standard deviation up and down is 68.26%. Remember that in Chebyshev, 2 standard deviation up and down was what? Let me go back to this. 2 standard deviation up and down is 75%. Empirical rule, 2 standard deviation up and down covers 95.44%. 3 standard deviation up and down practically covers everything, right? 99.72%, almost everything. So empirical rule is a stronger rule. I mean, in a way, empirical rule only applies for normal distribution, nice bell-shaped distribution. Distribution that looks like this. So that's why. But Chebyshev, we don't have to guarantee this nice bell-shaped curve. It works with any type of distribution. So I think that's basically why we have this price, the difference, right? Empirical rule and the Chebyshev rules. Okay. All right, we're going to continue on this from the second video. Okay.